Okay, so we're going to talk about volumes of surfaces of revolution. And let's first talk about how you create such a surface. Let's say, for example, you have a function. We'll start off with a simple one. Let's say we have square root of x. And so square root of x, it has a graph. And it looks like that. Now let's say we are going from 0 to 1. Okay, so this square root of x just stops right here at 1. Okay, now let's say that you rotate around the x-axis. So you grab this, and it's, imagine it coming out at you and going completely around. Then this would reflect across. And what shape would it form? Well, it would look kind of like a little bowl, right? Kind of like that. And since it's rotating around here, the x-axis, you're creating a circle at the end bit. And so our task is to find the volume of this shape. Now, this isn't a shape that you normally find the volume of. You don't have a formula for it. So we're going to do it using calculus. So let me show you a nicer picture. Okay, so here's our picture again. And so how do we find the volume? So the idea is that you take a slice at a point. So let's say you slice it right here. What would the cross section look like if you slice it right there? Well, it would look like a circle, right? And so, imagine this is a slice of a circle. So now what's the shape of that circle? I guess I shouldn't say what's the shape of that circle, but well, this shape, this is a cylinder, right? This is a cylinder, and it's located at the point, well, let's just call this x for now. And then right here, the thickness, let me erase this little arrow. Oh, I can't. Well, I'll just write over it. Okay, the thickness is going to be called delta x. Now, what's the, notice that, so this is, one part of it. And so what if I wanted to find the area of the entire shape? Well, you can look at this as a bunch of these little cylinders, right? So if we take a look at, if we have several of these, here we have an example of several different sizes. You can add them all up, and you would get, it would be an approximation of your area. But that's not what we're doing here. I mean, we didn't study calculus to just approximate. Check this out. This is amazing. Okay, let's say you wanted to find the volume of one of these discs. Let's call it disc CS, disc cross section. Okay, so well, it's a cylinder, right? So the volume is equal to I'm going to write it in a special way. The area times delta x. So what I mean by that is the area of the if you find the area of the circle portion, and then you multiply times delta x, that's delta x is kind of like the height of the little cylinder. So you always have the delta x in there. And so you have that the volume is equal to area, well, this is a circle, right? Pi times r squared times delta x. But now what's r? What's the radius? So from here to here, you need this to be in terms of your function. Well, what is that distance right there? This right there is f of x, right? It's the value of your function at that point. Okay, now, so let's do this. and you'll probably be able to guess in a little bit where I'm going with this. Let's call this point x sub I. So this is going to be the ith point where you're finding the cross section. So like these would be all the different ones. This would be, for example, the first and the second, third, fourth, and so on. You would have more, but you get the idea. And so this is going to be called f of x sub I. So then the volume is equal to pi times f of x sub I squared times delta x. Now, this is the volume of the cross section. So maybe I should put a little CS here, volume of the cross section. And so you can probably semi-guess where I'm going with this, because this is the volume of one cross section. And what we want to do is we want to find the volume of all of the cross sections, but that's an approximation. To take the approximation to be more exact, you take delta x and you make it infinitely small. So you make these little disks infinitely thin. Take delta x to go to 0 and add up how many of these little disks. Infinitely many, right? Infinitely many disks. Okay, let's write that down. So that's going to be the exact volume. So the exact volume is equal to the sum from 1 to infinity of the volume of the disks, right? So this is pi times f of x sub I squared times delta x. Well, what does this look like? This is exactly the formula for the Riemann sum. This right here, this is equal to the integral from, in this case, where are you going from and to? Well, I'll just write it as a to b of pi times f of x sub I squared times dx. And this right here, so okay, this part right now is really important. This right here, that represents the area of the cross section. Cross section. And so basically what you're doing, and then this right here, the dx, this represents the thickness of the cross section. And so basically the way to look at it, oh, geez, I guess I should have written just CS. But anyways, the way to think about it is that here, this right here, this is the area of a cross section. And then by multiplying it by the thickness, you're finding the volume. But these are infinitely thin, so it's like a wafer thin little discs. It's like these, but they're flattened to the point where they're just a flat wafer. And then you're just adding all of them up, and when you add them all up, that gives you the entire volume inside of there. Amazing, absolutely amazing that you can find that. So this is the sort of hidden power of calculus that up till now we couldn't really see, and this whole idea that you can just turn an infinite sum, and there are a lot of different tons and tons of applications of this, an infinite sum, and turn it into a relatively simple operation to do here. So let's do it in using our values. So we have that the volume for us is going to equal to the integral, and then from a to b, in our case, that's going from 0 to 1. Okay, and then it's going to be pi times f of x sub I squared. It's easier to think of this as just the area, because we're going to be looking at different kinds of situations. So this right here should be the area of a cross section. Okay, so because the cross section is a circle, let me go back to this. So the cross section is a circle. So the area of that cross section is pi r squared, and then r is the value of the function at that point. And so my function in this case is square root of x. So that's the that's going to be the radius at each x value. So it's going to be pi times the radius, which is square root of x, squared, and then dx. And then you just find the this integral. So let's just finish it off here. So this is the integral from 0 to 1 of, and I'm going to put the pi outside, and then square root of x squared is just x dx. And so this is equal to pi times x squared over 2, evaluated from 0 to 1, and so this is simply pi over 2. Wow, that's crazy. Crazy awesome.